Hello everyone, welcome to lecture number 8. This lecture we will study ratio test and problem based on ratio test. Ratio test is one of the important result to solve series questions. So let's write down the statement of ratio test. So if we have a series, so let sigma an be a given series. Let capital L is equal to limit as n goes to infinity modulus of an plus 1 upon an. Then number 1, if L is less than 1, then series an is absolutely convergent. We know that absolute convergence implies the convergence, or we may say that it is series an is convergent, because absolute convergence implies the convergence. So whereas the converse is not true, we have seen this with a counter example in the lecture number 7. So if the series an is convergent, if your value of limit that L is less than 1. Second part of the theorem, if L value is greater than 1, then series an is divergent. And the third remark of theorem, if L is equal to 1, then test fails. In that case, we cannot apply the theorem. The test is inconclusive. We will not prove this theorem, but of course we will have the problem based on this theorem. So let me quickly recall what I have written. It says that if you have a series an and you need to calculate this L, if you could calculate this L, then just check whether this L is less than 1, greater than 1, or equal to 1. If it is less than 1, then we can say that series is absolute convergent. If it is greater than 1, then we say that the series is divergent straight away. And if L is equal to 1, then the test straight away fails. That means you are not allowed to apply the test. So the question, check the convergence of following series. Check the convergence of following series. So number 1, sigma n plus 3 factorial upon 3 factorial n factorial 3 to the power n. Solution. Here your an is n plus 1 n plus 3 factorial divided by 3 factorial n factorial 3 to the power n. And an plus 1, just replace n by n plus 1, so you get n plus 4 factorial upon 3 factorial n plus 1 factorial 3 raised to n plus 1. Raised to n plus 1. So we have an plus 1, we have an. So let's find out the ratio of that an plus 1 upon an. So L is equal to limit as n goes to infinity modulus of an plus 1 upon an, which is same as limit n goes to infinity modulus of what is an plus 1 is this, n plus 4 upon 3 factorial n plus 1 factorial 3 raised to n plus 1 n plus 4 factorial. Let me take this here, let me take this here, this also here, so that n plus 4 factorial divided by 3 factorial n plus 1, 3 factorial n plus 1 factorial 3 raised to n plus 1, and an is nothing but n plus 3 factorial, denominator to denominator becomes a numerator, so 3 factorial n factorial 3 raised to n, modulus complete. So now I will not continue with mod because everything is positive here and modulus of positive is that number itself. There is a nice rule of factorial. Your n factorial is same as n into n minus 1 factorial. So n plus 4 factorial is equal to n plus 4 into n plus 3 factorial. So n plus 3 factorial in numerator, n plus 3 factorial in denominator will get cancelled. So we will have n plus 4 on numerator. N plus 3 factorial from numerator and denominator will get cancelled. Then this 3 factorial will get cancelled. Similarly, this n factorial and n plus 1 factorial. N plus 1 factorial is same as n plus 1 into n factorial. So n plus 1 and n factorial will get cancelled. So denominator will have n plus 1. 3 raised to n upon 3 raised to n plus 1. 3 raised to n plus 1 is same as 3 raised to n into 3. So one of the 3 raised to n will get cancelled. So we will have 3 in denominator. So it is 1 by 3 limit as n goes to infinity. If I take n common from numerator, then it will be 1 upon 4 by n. Similarly, from denominator, it will be 1 plus 1 by n. This n will get cancelled. So this is 1 by 3. As n goes to infinity, 4 by n goes to 0, 1 by n goes to 0. So this is entire bracket is 1. Now final answer is 1 upon 3. We could see that this 1 upon 3, L value is 1 upon 3, which is less than 1, implies that series AN is convergent by ratio test. Question number 2. Check the convergence of the series again. N goes from 1 to infinity, 1 minus 3 by n to the power n. Now here my n is 1 minus 3 by n power n. Let me find out the limit as n goes to infinity of an, which is same as limit n goes to infinity 1 minus 3 by n to the power n. If you remember, in 12th standard you have done one result, that is 1 plus x power 1 by x as limit x goes to infinity plus x, limit x goes to infinity, is always e. So this result I will apply here because this result will gonna help us to find out this limit. Limit n goes to infinity. Now this is same as 1 plus, this is same as 1 upon n upon minus 3 Now numerator n, let me divide it by -3. If I divide it by -3, then I can multiply by -3. Now this is same as limit as n goes to infinity 1 plus 1 upon n minus 3 raised to n upon minus 3 whole bracket to the power -3. Now here this is my basically x. So x and its reciprocal, you can say that this is full my x, and that is getting reciprocal. So this limit is straight away, this limit is e, so it is e to the power -3, which is 1 upon e cube. So limit of n is, as n goes to infinity, is 1 upon e cube, which does not converge to 0, and if the series is convergent, then its nth term must converge to 0. If the nth term does not converge to 0, implies series is divergent. That's one of the fundamental result of series, which we have done in the very first lecture. So this would imply series an is divergent. Example number 3, that check the convergence of series -1 raised to n cube upon 5 raised to n. So again we could see that an is straight away -1 raised to n cube upon 5 raised to n. B an plus 1 is -1 raised to n plus 1, n plus 1 whole power cube upon 5 raised to n plus 1. Is it okay? So let's find out the limit L, which is equal to limit as n goes to infinity modulus of an plus 1 upon an, which is same as limit n goes to infinity modulus of -1 raised to n and -1 raised to n plus 1. When I'm writing in modulus, that will be anyway becomes a plus, and so it is n plus 1 whole cube, n plus 1 whole cube upon 5 raised to n plus 1 upon n cube into 5 raised to n, and in denominator we will have -1 raised to n also, which is same as limit as n goes to infinity. I will remove the mod sign because natural number is positive, and that -1 raised to n plus 1 becomes positive. You could see that one of the 5 raised to n will get cancelled, so we will have 1 upon 5 and n plus 1 upon n whole cube, which is same as 1 by 5 limit as n goes to infinity 1 plus 1 by n whole cube. As n goes to infinity, this is basically 1 plus 1 by n 3 times. So limit of a into b is same as limit a into limit b. So you could see that this is limit of 1 plus 1 by n is 1. So multiply by 3 times. So you will have that 1 into 1 into 1. So 1 by 5 times 1 into 1 into 1. So finally you'll get 1 only. You'll get 1 into 1 by 5. So that is 1 by 5. So L value is 1 by 5, which is less than 1. That would imply series AN is convergent by ratio test. because ratio test says that if your limiting value is less than 1, then we can straight away say the series is convergent. Now not only convergent, in fact it is absolute convergent. That one need to add it. And this is question number, I think question number 3 I have done. Now let's have the question number 4. That is the last question of this lecture. Series 2n factorial, 2n is in bracket, upon n factorial, n factorial. So let's find out L, which is limit n goes to infinity modulus of an plus 1 upon an, which is same as limit n goes to infinity. Now you could understand what is an. An is basically 2n factorial upon n factorial, n factorial. So let's find out an plus 1. So it is 2n plus 2, n replaced by n plus 1, so 2 will be multiplied, 2n plus 2 factorial divided by n plus 1 factorial, n plus 1 factorial. Then an is as it is, 2n factorial, n factorial, n factorial, modulus complete. So 2n plus 2 factorial is same as 2n plus 2 into 2n plus 1 into 2n factorial. So 2n factorial and 2n factorial will get cancelled, but I will have 2n plus 2, 2n plus 1 and 2n factorial, that will get cancelled. N factorial and n plus 1 factorial, we could see that this n plus 1 factorial is same as n plus 1 into n factorial, and n factorial from the numerator will get cancelled. So we will have n plus 1 into n plus 1. Of course, limit as n goes to infinity. Now from both the brackets you can take n common and you can cancel out that. So 2 plus 2 by n we will have, and similarly here it is 2 plus n we are taking common, 2 plus 1 by n, denominator 1 plus 1 by n, 1 plus 1 by n. So from numerator denominator we have taken n square common, so it get cancelled. So as n goes to infinity, this goes to 0, this goes to 0, this goes to 0, this goes to 0. So numerator will be 2 plus 0 into 2 plus 0, that is 4, and denominator will be 1 plus 0 into 1 plus 0, that is 1 plus 1 into 1, so we will have 1. So this answer, this will give you 4, which is greater than 1. So L value is greater than 1, implies series an is divergent by ratio test. This completes the lecture number 8. In next lecture we will see the root test, and then one lectures of unit 1, that is from the mean value theorem. I will just revise one lecture and then your syllabus will end. Thank you.